Okay, in this video we're going to have a look at the coupled pendulum. So we already had a look at quite a few examples now, and hopefully from the last example with the sliding pendulum we saw how important it is to understand Lagrangian mechanics, and that Lagrangian mechanics simplifies the calculation process quite a bit. So here we're going to go through another example where the advantages of Lagrangian mechanics become apparent. So let's dive into it. So let us say we've got this is green. Let's say we've got a wall, and then we have two pendula, one like this. Well, actually let's draw it in this way, one like this and one like this. Here we have mass 1 and here we have mass 2, and these two pendula are connected with a spring. So the length of the first pendulum, let us say, is L1. Actually, let's just say it's L because we're going to assume that both pendula have the same length. And then the angle subtended by the first pendulum with the vertical is theta 1, and the angle subtended by the second pendulum is theta 2, and we're interested in finding the spring constant is K, and we're interested in finding the equation of motion. Now we're going to make a small approximation. We're going to say that theta 1 and 2 are small. So basically cosine theta 1 is roughly 1. Well, cosine theta 1 is roughly 1, and cosine theta 2 is also roughly 1, and sine theta 1 is roughly theta 1, and sine theta 2 is roughly theta 2. We're going to make these approximations because it simplifies the calculations quite a bit. Because if these two pendula are at different heights, if the displacement of the angle becomes too large, then you're going to get situations where the spring is going to be like this in a diagonal position, and that's not what we want. That complicates the calculation quite a bit. So we are just going to assume that theta 1 and theta 2 are very small. Okay, let us calculate the equations of motion. So remember, the equations of motion come from the Euler-Lagrange equations, and now we have two dynamic variables. We have theta 1 and theta 2, and we have obviously theta 1 dot and theta 2 dot. So let us first, remember the Euler-Lagrange equations are basically d by dt partial L partial theta 1 or 2 dot is equals to partial L by partial theta 1, right? So let us calculate and remember the Lagrangian is just the kinetic energy minus the potential energy. So let us calculate the kinetic energy first. Well, the kinetic energy is just going to be 1/2 m1 v1 squared plus 1/2 m2 v2 squared, right? And the potential energy is just going to be the height of the problem. So it's just going to be m1 g1 times h1 plus m2, not g1, only g here, plus m2 times g times h2, right? So how do we calculate? We need to calculate v1, v2, h1 and h2. So to calculate v1, v2, h1 and h2, we're going to first look at the position of the pendula. So the coordinates of the first mass is basically the x coordinate. Let us say we put the origin over here, so this is y and this is x, and here we have 0. Then this one is going to be minus capital X minus capital X1, and this one is going to be plus x2. Well, the distance is always positive. right? So the position of the first mass is just this position plus this distance, right? So it's going to be minus x1 plus, and then it's going to be L times sine theta 1. L times sine theta 1. And the height, we assume that this support is at the height h. Then the height is just going to be the height h minus this distance over here, which is L times cosine theta 1. So this is h minus L times cosine theta 1. And similarly for the second mass, we have plus x2, and then we have plus L sine theta 2 and h minus L cosine theta 2, right? So we have the position. Now let's calculate the velocity. So we calculate r1 dot is equals to what? Well, first, this x1 is a constant, L is a constant, so we only have to differentiate sine theta with respect to time t, and we use the chain rule because theta 1 is a function of t. So this is going to give me L times cosine theta 1 times theta 1 dot. And the y coordinate, h is again a constant, L is a constant, so this is going to give me sine theta 1 times theta 1 dot. Because, well, L times sine theta, because the cosine differentiate gives me minus sign, so the minus cancels, and that's it. And we can also calculate the position of the second one, which is just going to be L times cosine theta 2 dot, and L times cosine theta 2, sine theta 2 times theta 2 dot. This is the position of the second mass. And now we're ready to calculate the kinetic energy. So the kinetic energy is just 1/2. So the kinetic energy is 1/2 m1 r1 dot squared plus 1/2 m2 r2 dot squared, and that's just half m1. Now we square each of the components and add them up, so that's going to give me m1 times L squared cos squared theta 1 dot squared plus L squared sine theta 1 squared theta 1 dot squared. And similarly for the second mass, we have 1/2 m2 L squared cos squared theta 2 dot squared plus sine theta 2 squared theta 2 dot squared, and we forgot a square over here. So that's just going to be 1/2 m1. Now we have a common L squared and theta 1 dot squared in here, and the cosine squared and the sine squared add up to 1, so that's going to be L squared theta 1 dot squared, right? And the same thing for the second mass, m2 L squared theta 2 dot squared. So this is the kinetic energy of the system. I made a small mistake in the potential energy of the system because it's not just the height, because now we also have a spring here. So we're gonna have to add another term here, the potential energy due to the spring, and that's just gonna be 1/2 k x1 minus x2 squared. And the reason for that is, suppose we move both m1 and m2 by the same amounts towards the right or towards the left, then the spring is not going to be elongated or contracted, right? So there's no potential energy. But if we so so that already tells me that if x1 and x2 are equal, then you're not going to get any term for any contribution to the potential energy. If, however, we move the first one to the right and the second one to the left, this one in this direction and this one in this direction, then you have to add up the displacement. So you get x delta x. If x1 is delta x and x2 is minus delta x, then you get 2 times delta x. So that's exactly what we expect. And the square is there because this is the nature of a spring, right? So it's k times x1 minus x2 squared. So let us calculate now the potential energy. We said that the potential energy is equals to, let us copy it from here. I'm going to copy and we're going to paste over here, right? And now h1 is just the height of the first pendulum, so that's m1 times g times L times cosine theta 1. Well, it's actually, sorry, it is H minus L times cosine theta 1. Let me just check that over here. 1 H L times cosine theta 1, yes. And this second term gives me M2 times G times H minus L times cosine theta 2, right? And then the final term, which is 1/2 k times, and then x1 is just minus x1 plus L sine theta 1 minus x1 plus L sine theta 1 minus x2 minus L sine theta 2. Now this x2, these are the initial displacements. These are the displacement of the support, right? So basically, yeah, that's it. This is the potential energy. And now we're almost done. Now all what we need to do is calculate the equation of motion. So we've got the potential and we've got the kinetic energy, and we have the potential energy over here, right? And the potential energy. So now all what we need to do is calculate the equation of motion. So remember, for the equation of motion, we have got where is it? Didn't I write it down? Over here. We got the Euler-Lagrange equations. The Euler-Lagrange equations, right? So once we do it with respect to theta 1, and the second time we do it with respect to theta 2, right? So where do we have theta 1 dot dependence? The only place where we have theta 1 dot dependence is in the kinetic energy of the first pendulum. And the only theta 1 dependence we have in the potential energy, right? Now, okay, let us calculate this. So we first do the equation of motion for theta 1. So we have d by dt, d by d1, d by d theta 1 of kinetic energy. Here is the only theta 1 dependence. Here we have no theta 1 dependence, so that falls away. So we have 1/2 m1 L squared theta 1 dot squared, right? And this is supposed to be equals to d by d theta 1 of, and then this guy with respect to theta 1. And the only term, remember that we assumed that theta 1 was very small. Theta 1 and theta 2 are small, so this is going to be roughly equals to 1, and this guy is also going to be roughly equals to 1, right? And this one here is roughly theta 1, and this one here is roughly approximately theta 2. So yes, so the only theta 1 dependence is in 1/2 k L, sorry, this should be squared. This should be squared, yes. Yes, this is squared. So we have to, I'm sorry, we have to, this is going to be a bit more lengthy. So this is equals to d by d theta 1 of 1/2 k minus x1 plus L sine theta 1 minus x2 minus L sine theta 2 squared, right? And now we can evaluate this. So this basically gives me, if I differentiate this term with respect to theta 1, the only thing that remains is 2 theta 1 dot. So I get d by dt 1/2 m L squared theta 1 times 2, right? And this is equals to, I use the chain rule now. So this gives me 1/2 k. The 2 comes down and what remains is a 1. So we have 2 times minus x1 plus L sine theta 1 minus x2 minus L sine theta 2. And then the chain rule. So of course I forgot that this is roughly theta 1 only. So this is theta 1 and this is L times theta 2. So here we have L times, theta 1 and L times theta 2. And if you differentiate the composition with respect to theta 1, we just get times L, right? And now what we can do, this should be theta 1 dot, sorry. So if you now take the left hand side, differentiate with respect to t, the halves are going to fall away. The half falls away. M and L squared are constants. Theta 1 is the only one depending on time. So we get M L squared theta 1 double dot. And this is equals to, here the half falls away as well. This is just equals to k times L. And then we have minus x1 plus L theta 1 minus x2 minus L theta 2, right? So yeah, that's the equation of motion for the first pendulum. You can do the calc for theta 1. You can do the same. Well, actually we can simplify this a bit. This L squared falls away and then we're left with M theta 1 double dot is equals to minus x1 plus L theta 1 minus x2 minus x2 plus minus L theta 2. And yes, what we assume now is that if theta 1 and theta 2 are both 0, then the potential energy is 0. So in other words, the equilibrium length of this pendulum is exactly the distance of the two supports, x1 plus x2, right? So we can actually ignore these two terms over here, this one and this one. So we get M times theta 1 double dot is L times theta 1 minus theta 2, right? We can do the same thing for now we do the same thing for theta 2. For theta 2, we get yes, the only theta 2 dot dependence here we take this equation here and do the calculation for theta 2. So the only theta 2 dot dependence is again in the kinetic energy over here. So we get 1/2 m2 L squared theta 2 dot. So we have d by dt 1/2 m L squared theta 2 dot squared, and all of this is differentiated with respect to theta 2. So I'll write this again. d by dt d by d theta 2 1/2 m L squared theta 2 dot squared, and this is equals to the derivative with respect to theta 2 of the potential energy, and the only terms depending upon the potential energy in the potential energy with respect to theta 2 is these terms fall away again because they're constant, and the only term which remains is this potential energy of the spring. So again, yes, that's this term over here. Copy, paste, right? Right, so then we get d by dt, and now we differentiate this with respect to theta 2, so we get 1/2 m L squared 2 theta 2 dot, and this is equals to 1/2 k 2 minus x1 plus L theta 1 minus x2 minus L theta 2 times the inner derivative using the chain rule. We get minus L, and this simplifies further. We can cancel the 2's over here. We can cancel the x1, the equilibrium distances, and then we get d by dt m L squared theta 2 dot is equals to 2 cancels minus KL. Remember, we have the minus over here, and then we have L times theta 1 minus L times theta 2, and then over here m and L squared are constants, so the only thing depending upon is theta 2 dot. So we get m times L squared theta 2 double dot is equals to minus k L theta 1 minus L theta 2, and the L squares cancel, and what you're left with is m times theta 2 double dot is minus k theta 1 minus theta 2, and I think there might be a mistake with the L. Yes, there was a mistake with the L in here. Basically, yes, there still is an L over here, and that one cancels with this one, with these ones. So we don't have an L here. So you see, as you can see, the equation of motion is very similar to that of the theta 1, except that we have a minus sign over here. So let me write down both the equations again. This is the second one. Whoops. This is the second one, and the first one is this one. This is the first equation of motion, and this is the top one is the second equation one, right? So this is a interesting problem. It looks very similar to that of the harmonic oscillator, and actually is, but it's not exactly the same. So what we're going to do is, maybe we're going to have a look at the solution of this equation in some other video, in some future video, but for now this is enough. So there should be a k here, obviously. So yeah, we're gonna have a look at the solution to this equation in a future video, and that's it for now. Thank you for watching. Please subscribe. I have much more videos like this coming up, and I hope to see you in the next video. Thanks. Bye.